Hi, in this video, I'll be solving this question right here, problem 1 from day 1 of the IMO from this year, 2023, the International Math Olympiad. The problem says, determine all composite integers n greater than 1 that satisfy the following property. If d1, d2, dk are all the positive divisors of n with 1 equals d1, and then d1 is less than d2, less than all the way up to dk is equal to n, then d sub I divides d sub I plus 1 plus d sub I plus 2 for every I between 1 and k minus 2. All right, so to solve this problem or any problem, whether an Olympiad problem or a regular classroom problem, you should always spend some time exploring or strategizing. So I have the first divisor is d1, and then the next smallest divisor is d2, all the way to dk minus 2, k minus 1, and dk, which is the same as n. Well, d1 is equal to 1, so it doesn't count. d2 is the smallest divisor, so it has to be a prime. So this is going to be equal to some sort of prime number p. Well, up here you have dk minus 1, and it is the largest proper divisor. The missing factor has to be the smallest divisor. In other words, dk minus 1 times p has got to be equals to n, or dk. And likewise, dk minus 2 is the second largest divisor. So the missing factor, the factor that it would multiply it to n, has to be second smallest divisor. So this one multiplied by d3 has got to be equal to dk, and etc. all the way back. I'm going to write it on the side here that di times dk minus I plus 1, I guess, is equal to n. I don't know if it's useful yet, but I'm going to save it there. That gets me the information I can get out of this. So now I have this extra information here, or condition here, that di has to divide di plus 1 plus di plus 2. One has to divide the sum of these, which is kind of obvious. P has to divide the sum of these two. And that's interesting, but I don't know anything about D3 and D4. So I'm not going to work with the low end of this chain. I'm going to work with the high end, because I do know that this divides that. So dk minus 2 must divide dk minus 1 plus dk, which is equal to n. And dk minus 2 already divides n. Therefore, it must also divide k minus 1. So dk minus 2 must divide dk minus 1. That means there's some factor f that must multiply from dk minus 2 to dk minus 1. Well, once I get there, it feels weird. It's not quite wrong, but there's something not fitting correctly. Because this is the smallest divisor, and this is the second smallest divisor. Then where does this factor f fit into this? Because remember, f is a factor of n as well. So this is a divisor, this is a divisor, this is a divisor. And between the three of them, they have to fit in two spots. Pigeonhole principle says that two of them got to be the same. Well, D2 and D3 cannot be the same by hypothesis. F and D3 cannot be the same because F is a proper divisor of D3. And therefore, F and P have to be the same. F, P, and D3 must fit in D2, D3. And since F cannot be D3, that means F and P must both be equal to D2. That factor over here has to be a P. That means D3 is a P squared. And I suspect, therefore, that it's gotta be all powers of P here. Because I feel like if I go backward again, I have the same pigeonhole principle problem again, that there are more factors in existence than there are places for them to fit. That's going to be my strategy. My strategy is to prove that all the i's are powers of P. All right, now that I know my strategy, I can go ahead with the proof. Well, it turns out that when I was strategizing, I was thinking in terms of pigeonhole principle, but when I sat down with the formal proof, using that didn't help me. Maybe some of you can do it. So I ended up doing it differently. So here's what I'm claiming. My claim is that each di is a power of a prime P. Well, specifically, I know that the first proper divisor, D2, is a prime. And all the other D's are powers of it. So it's specifically power I minus 1. Well, I must prove both ways, both if and only if. The easy one is the sufficient condition. If D is a power of a prime P, then it fits all of these conditions. That's kind of obvious. So clearly sufficient. And also the other condition. Actually, I need to add over here as part of the claim that, because the question is not about the di, it's a question about the n. The necessary condition is the harder part. I'm going to do it in 2 steps. Step 1 is that D2 is equal to P, D3 is equal to P squared. And step 2, I'm going to prove that that there are no other forms of D sub I. Right, so step 1. D2 is the smallest proper divisor, so it has to be a prime. And dk minus 1 is the largest proper divisor. And so dk minus 1 must be missing the D2 factor. Now dk minus 2. So on the one hand, dk minus 2 is the second largest proper divisor. And therefore, dk minus 2 times d3 is equal to n. But also, dk minus 2 divides dk minus 1 plus dk, which equals to dk minus 1 plus n. And dk minus 2 already divides n, therefore it must divide the other term as well, dk minus 1. Well, that means that there exists an f such that dk minus 2 times f is equal to dk minus 1. And then we multiply by p both sides, dk minus 2 times fp is equal to n. Well, this part is equal to D3. That means F, P are both less than D3 and are both greater than 1 as well. And are divisors of n. Well, there's only one. And that is D2, so the two of them must be D2. And therefore, D3 is equal to P squared. On the actual IMO, I'm pretty sure you can do this with a lot less words. So that was step 1, where I proved that D2 is equal to P and D3 is equal to P squared. Now I proved that there's no such other form of D sub I. Step 2. Suppose there is a D sub I that is not a power of P. If there's one somewhere, there's got to be the first one. So let's take that first one. Suppose that there is the first D sub I that is not a power of P. Then this D sub I has to be a prime. Otherwise, a non-P factor of D sub I would be a smaller divisor of n that's not a power of P. So yeah, when I say divisor, I mean divisor of n. Well, then let's look at the D's that come before this D sub I. Then you have D sub I minus 2 is a power of P. And this P to the power I minus 3 divides P to the power I minus 2 plus Q. Which means P to the power I minus 3 divides Q, which is a contradiction. QED. And the answer is that the composite number n must be a power of a prime. Well, that's been fun. Hope you had fun too. Any question or thoughts, put it in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.